Good evening and welcome to Kopernik Observatory. It's great to have a nice crowd here this evening. My name is Drew Desker. I'm the director here at Kopernik, and I'm really looking forward to tonight's program. Before we get started here, let's see who is here for the first time or hasn't been here since your 4th grade field trip. Wow, okay, a fair number of people, good. Then who here are members? Okay, pretty much the other half. So actually, the people who raise their hands second have this valuable tool in their wallet. It's their Kopernik membership, and not only can you get in on into Kopernik on any Friday night and for certain special occasions for free, but also we belong to what's called the ASTC, Association of Science and Technology Centers, and it's a consortium of 380 or so science centers throughout the country, but also international, that honor each other's memberships. So your Kopernik membership here gets you into Roberson, gets you into the Museum of Science and Technology up in Syracuse, gets you into the Intrepid down in New York City, all for free. And you skip the long line trying to buy your day ticket. So if you like this kind of place, you might want to consider getting a membership. So we are actually celebrating our 50th anniversary as a STEM education and the public observatory here in the Southern Tier. Back in 1973, the building was starting to be built. We actually opened in June of 1974. And later this year, we will actually have a big 50th anniversary gala down at the Doubletree in October. The keynote speaker is Nobel Prize-winning Sir Dr. Stanley Whittingham from Binghamton University. And we'll be also announcing some exciting plans to sort of set us off on our next 50 years. Up on the screen here is our website. We always keep it up to date with what's going on. So obviously you can tell tonight we're going to be talking about drone swarms. But also you scroll down and you'll find out that we are actually in the middle of our summer camp season. Today we just finished our second week of summer camps. We were having 2nd and 3rd graders learn about the secrets of code. And we had middle schoolers building rockets. And there were some, I guess you could call them, they started out with air rockets and moved into some sort of commercial, Estes kind of rockets. And then they sort of built their own. I call them Frankenstein kind of, and they flew much like remember some of those Far Side commercial Far Side rockets, they were all spinning and all that. Well, they had a few of those this afternoon as well, but the kids learned a lot from it and had a great time. We've got other camps coming up this for the rest of the summer. We've got one coming up called Welcome Aboard the International Space Station. And these are rising 5th and 6th grade students that will be learning what kind of training astronauts go through, what kind of work they do on the ISS. We talk about satellite orbits and radio communication, and our students will actually have an opportunity to talk to an astronaut on the International Space Station as they're flying by, using the ham radio station we have here. And that will actually be live streamed on our YouTube channel. So. If you want, you can check that out. We'll also do another. We're doing some. We've got a camp on virtual reality, augmented reality for middle schoolers. So a lot of good stuff going on. But beyond our summer camps, our Friday night programs are really what I really enjoy because it's an opportunity to do really lifelong learning, and so especially for some of the younger people in here. School doesn't end at 12th grade, all right? It's something you do all lifelong, and you really get to learn some neat stuff. And so we try to do that every Friday night from March to mid-December. So back in 2020, we had to sort of stop because of COVID. And we figured, okay, well, we'll just wait, a couple of weeks for this COVID thing to blow over, and didn't exactly play out that as we had hoped. But so we said, look, we got all these speakers lined up. Why don't we do something? And so we started live streaming. We had those speakers actually zoom into us. We then put it out on our YouTube channel. And when say hello to those watching on the YouTube channel this evening. We now have over 13,000 subscribers to our YouTube channel. So not only do they watch our Friday night programs, but we'll do live stream astronomy. We've done lunar eclipses. We've done meteor showers. We actually did do a solar eclipse, although it was more of a clouds eclipse. But we were ready. And but you know, again, looping back to Friday night programs, it's really an opportunity for us to find out, what's happening in technology. But also, I like it because it's an opportunity to find out what's happening here in the southern tier. We're very fortunate to have, again, a very long history of technology development, starting with IBM, with SingerLink, now Lockheed BAE L3. We have a world-class university that does extraordinary research, and we've had numerous faculty up here. In fact, we've even had Dr. Whittingham up here prior to his Nobel Prize, but still talking about his work developing the lithium-ion battery. However, you didn't come here to hear me talk about all the good stuff we do here. We came here to talk to listen to Dr. Jayson Boubin, and we're very fortunate to have him talk about his work. So I'll invite you to come on up. You want to turn your microphone on, if you would?
Yes.
You are?
Learn how this works.
2 switches. Up top.
If only I could find. Up top. Okay. So as. Oh yeah, of course. So I'm a very loud speaker. So if I blow your ears out, I apologize. Drew has promised that he will turn me down if necessary. But thank you again for the kind introduction. So my name is Dr. Jayson Boubin. I am an assistant professor at Binghamton University in the computer science department. And I'm here to talk a little bit about my research into UAVs. So I've been working with UAVs since I was a teenager. They really captured my imagination back then and allowed me to sort of experiment with my appreciation for computers and for robots. They're just very cool, right? But when you work with these kinds of things, you always want to think, what can I do with these to actually help society? How can I use my talents to at least attempt to make the world a little bit better? And that's what I want to talk about today. I want to talk about the intersection of this specific type of technology, of UAVs, UAV swarms, and artificial intelligence, which we've been hearing a lot about, and how we can use those things to help make the world a little bit better. So to begin, I want to ask you all a bit of a question. This is rhetorical. You don't need to respond. But I want you all to think about what do you think of when you think about drones? When you see drones or when you hear the word drone, what does that make you think about? And I have a couple things that it makes me think about, and I want to challenge those assumptions, those immediate ideas that pop into your head. So a couple examples here. One that I really like. This is a video from a movie that came out in 2019, Spider-Man: Far From Home. I watched this movie. I really like this movie. And a big feature in this movie are these UAVs that, as we see Jake Gyllenhaal here, is using to presumably try to thwart Spider-Man. And as you see this drone right here, it looks pretty menacing, right? It's pretty, it looks dangerous, looks scary. It looks like a weapon. And we do use UAVs as weapons, right? That is the major thing that I think of personally when I think about drones. I think about drones like this, all right? And that's not personally what I like to build. Now, we also can use drones for other, maybe more innocuous things, right? So this is an example from not this 4th of July, but last 4th of July over presumably New York City. This is, I believe, in down by the Hudson Bay, or not the Hudson Bay, but down by the lower Hudson. So this is a UAV swarm that's performing a light show, right? It's looking like the Statue of Liberty. And these are all these little lights that you see out here. These aren't fireworks. These aren't anything else. They're drones that are they're being controlled not by humans but by automation. And they're able to do these very interesting, very beautiful light up shows, right? Very nice. Now, we also see UAVs that can make videos like this, where you can fly very quickly over a very interesting landscape. You can use these to film things in movies. We often see, if you start to notice this, you'll see it in every movie you ever watch, that we now see a lot of drone photography, right? And you can use it to capture very interesting shots, right? So this video is over the Portuguese island of Madeira, and it's a pretty inaccessible place, right? It's very craggly, very forested, but we can get in there with a UAV, right? But at the end of the day, what we're doing here is either, in these examples, entertaining ourselves or potentially hurting people, right? So are there other things we could do with drones? Now, probably most of you who have a drone, and I will ask for a show of hands, does anybody here own a drone? Does anybody have one? Okay, a few people have one. Now, probably, and this is a very common concept, when you get a drone, maybe you got it for Christmas, right? Maybe 9 a.m. you opened up your drone. Probably around 11 a.m. it looks a little something like this. So, how many of you have crashed a drone? Has anybody here crashed a drone? Okay, a few people crashed drones before. I crashed lots of drones. Less now than I used to as a grad student and as a younger student. But this is very common, right? Drones crash all the time, but this is something that you'll see, right? They're pretty hard to control, crash all the time. But this is the average experience. Now, what I want to bring, I said I wanted to sort of reshape or challenge some assumptions about UAVs, and really, when I think about UAVs, I do think about weapons, and I think about entertainment and the value they provide in those regards, or not necessarily value, but I want us to think about the attributes that UAVs have and how those attributes can be used to benefit us, right? So UAVs are very good at coordinating with one another. So we can see the UAVs I have here. These are relatively big, but they can communicate with one another. We can instrument them with hardware that will allow them to talk, like your computer talks to your router or to other computers across the internet. That's a very real technology that we have the ability to implement on these drones. But we use them for things like light shows, right? This is basically the state of the practice with UAVs in at least the modern sense, or in the modern sensibility. Is this the best use of this particularly powerful technology? I ask you that. Now, we can also use UAVs for sensing. And when I say sensing, I mean that these UAVs have sensors on them, and those sensors are things that can pick up information about the environment. They're cameras. They could be LiDAR. They could be even, I have a hyperspectral camera there, which I'll talk about in a little bit. But what do we use these for? We use them for things like making drone videos, right? We capture these very entertaining videos. Maybe we use them to make movies. But is this the best we can do? Can we do something better with this technology? And we can also instrument intelligence on board these UAVs. So I'm going to talk a little bit about AI today. AI is something we hear a lot about in the news and something that I think is very misunderstood or misrepresented. But we can make our UAVs intelligent. And what do we do with these UAVs? Oftentimes what we do is we make them dangerous or use them for surveillance. And I'm not here to debate whether or not this is a valid use of this technology, but I do want to challenge this. I want to say, are these the best things that we can do with the devices I have in front of me? So I'm going to pose a problem. I'm going to pose a problem for you that I think UAVs can help with. Not solve, but help solve parts of. And that's climate change. Hopefully everybody in this room knows a little bit about climate change, but just as a quick introduction, climate change is directly caused by our human activity as we burn fossil fuels to power our houses, to power this room, to power our cars. We release greenhouse gases like carbon monoxide and methane into the atmosphere that over the last 250 years since the beginning of the Industrial Revolution have warmed the planet, right? So we see this increase in temperatures by a couple degrees Celsius. You might think, oh, that's not very much, but it's enough to cause some serious issues. One big problem that I'm very interested in, and hopefully you can see that down there, is that climate change leads directly to decreases in crop yield. So I don't know about you, but I like to eat. I do eat food. Hopefully all of you do as well. And almost all of that food either comes directly from a crop field or is fed by something that comes from a crop field, right? And climate change is directly impacting these yields. Now, I'll talk a little bit more about why this is a problem and how we solve it, but the way you should think about this is that as the sun beats down hotter on these crops, as stronger storms come and blow the crops over, as they get flooded with rain from typhoons and hurricanes like the ones that we just saw last week, or the heat wave that we just had last week as well, these crops wither, they lose their yield, and they are not harvestable. So this is a serious issue. This is something that we can use drones to potentially assist with. Now, we also have, as the climate changes, an increase in invasive species. So even in Broome County, we're experiencing invasive species. We have the spotted lanternfly here, which is my mortal enemy. We'll talk about that in a bit. We have knotweed. We have water chestnut. We have all sorts of invasive species here These aren't directly attributable to climate change, but invasive species, there's an increase in invasive species as our planet warms, as biomes change. Plant life and animal life move to different areas that they may not have natural predators, and then they flourish maybe to our detriment. So can we use UAVs to assist with this problem? Can we use UAVs to identify and eliminate invasive species? And last but not least, of course, we have these dangerous natural disasters, these forest fires that are occurring, stronger hurricanes. Can we use UAVs to assist with disaster response or with identifying these disasters as they occur? These are the questions that I want you to think about. Now, back to these attributes, these very important attributes that UAVs have. With coordination, this is a serious benefit, right? If UAVs can coordinate with one another, they can cover large areas, right? If I want to model crop yield in a cornfield, or I want to map a wildfire in California, I'm going to need to cover a large area here. And UAV batteries are relatively short-lived. Now, that's by the sort of physics that governs them. But if we can have many UAVs that can coordinate across a large space, that could be a significant benefit. Now, UAVs, as I mentioned, are also very good at sensing. We can put very interesting sensors on board these UAVs, and we can use those sensors for real-time analytics. I can, if I have enough intelligence on board the UAV, or I have the right algorithms, I can do things like model crop yield from the air in real time. Or I can detect forest fires with a thermal camera in real time. Or I can detect algal blooms with a hyperspectral camera in real time. These are very important applications. Now, with onboard intelligence, we can do things like actually detect individual objects. I can figure out if what I'm looking at through my UAV camera is a cat or a person or a spotted lanternfly with just a little bit of artificial intelligence, and we can have our UAVs pilot themselves. Now this, you might not think this is a UAV. This is a UAV that's navigating a space by itself. This is actually just the rendering of the map that it's building. But using proper artificial intelligence, we can actually allow our UAVs to navigate their own environments without human pilots. And these are a few of the things that I'm going to dive into today. But before I do that, I do want to give sort of a 101 lesson. I want everybody to understand, if you leave this room tonight, I want you to know how a UAV works, what the basic pieces are. They're basically like expensive Legos. How you can more or less put them together. And you can do this in your garage or your basement. I was doing this in my basement when I was 18. And loosely, how they work, how they fly. So let's start with that. We're going to talk about that. We'll talk a little bit about artificial intelligence, just so we understand it. And then I'm going to talk about a few things that we do in my lab to help solve some of these problems. So to begin, UAVs, there's a bit of a strict definition for what a UAV is. A UAV is any device that can fly without a human on board. So that means that if you had a Boeing 737 and you were able to instrument it with some autopiloting, that could be a UAV. If you had something the size of a bumblebee or smaller and it could fly without a human actually sitting on board, that could be a UAV, right? UAVs are controlled via a number of different mechanisms. We can have them fly themselves. We can control them with little remote controllers. But at the end of the day, there's no human on board, then this is a UAV. UAV stands for unmanned or uncrewed aerial vehicle, but we often, in modern parlance, call them drones. So these are the basic components of a UAV, and we're going to go through these one by one and talk about how they work and why they're important. But at the very base of the UAV, we have the propeller and the motor. These are what allow our UAVs to fly. We're going to talk about how that works, but you can see these spread out on the UAVs I have in front of me, and they're pretty mean, right? They spin pretty fast. If you start powering them up and you get your hand in there, you get a little cut up. I definitely have some scars on my hands from catching UAVs over the last 10 years of doing this. But these are what make these devices fly. Now, we also need a power source, right? We need to spin these motors somehow. And we'll talk about how they spin. But we need some power source. And we have the lithium polymer battery. This is, if you were paying attention earlier, Stan Whittingham, one of Stan Whittingham's contributions that won him his Nobel Prize, or particularly the lithium-ion battery, but it's a derivative of that. So we usually use these lithium polymer batteries, which I have one right down there. I actually have a few more in the bag as well. But all of this is controlled by an onboard computer. So we don't just have these motors spin however they want, right? We have to spin them in very specific ways so we can actually have the UAV follow a trajectory. And this trajectory is just the path, the planned path that the UAV will follow to do whatever it is we want it to do. We'll talk a little bit about that later. Now, one other important aspect of the UAV is telemetry, something that probably the people here at the Kopernik know a lot about. If they're communicating with the International Space Station. This is just a big fancy word for sending data over a distance, right? So I'm going to send data from point A to point B via telemetry, and drones use a lot of telemetry devices. They use GPS. They have remote control receivers. So if I have one of those little RC controllers, like you would control a car or a drone, you can control your UAV that way. We can also control drones over Wi-Fi. Many drones will use Wi-Fi or other more exotic RF spectra. And last but not least, these drones have cameras, right? These cameras are very important, and we'll see that these are vital to this intelligence that we can impart into the UAVs. That these sensors allow us a very rich perspective of our environment that we can do a lot of interesting things with. Now, to these components, I have this very blurry picture of the propeller for this drone that I have in front of me. And I want to talk a little bit about how this works and how it spins. So many of you probably know that we can generate thrust via the Bernoulli principle. This is just how airplane wings work. But we need motion, right? We need these wings to move forward or to spin somehow to actually generate thrust. And the way that we do this is actually via electromagnetism. So you might not think of electromagnetism as sort of fundamental to UAVs, right? But all of these motors that I have in front of me all contain electromagnets, right? So electromagnetism is one of the 4 fundamental interactions in physics. One other one that you might know is gravity and the strong and weak nuclear forces. And electromagnetism is very, very useful. We use it all the time in, I guess, in electrical engineering, not necessarily in computer science in my field, but very important interaction. At the very basis, electromagnetism is based on this concept that any charge, right, any electric charge that you would have fundamentally has a magnetic field associated with it. Now, what we can do is target that magnetic field into a specific direction. So if you think about those magnets that you might have at home on your fridge or that you might see in cartoons that look like those big U-shaped things with the North and South Pole, we can make those magnets out of just some very simple things that you might have at your house. So you can use a battery, a wire, and you don't actually even need an iron nail for this to create a magnet. All you have to do is run a wire from the positive terminal to the negative terminal of your battery and wrap it into a coil that we call a solenoid. Now this solenoid aligns the charge. It basically compounds that magnetic field from the charge in the wire to direct it into a north and south direction that we can then use to magnetize things. We can actually connect things or put things into that magnetic field like these paper clips. Having an iron nail in there just reinforces that magnetism. Iron is ferromagnetic, so we can align the dipoles and make the magnet stronger. So most of our UAV motors have many electromagnets in them. I think these ones have 20 electromagnets in them. And we use these to actually spin the motors. So how does that work? Well, the general idea is that we have this concept of the brushless DC motor. And the idea behind this, don't worry about what the brush is. It's just a spinning part inside the motor. But the idea here is that we use electromagnets to spin the motor. So we have these electromagnets right around here. They're called stators in this case. So a motor has 2 pieces. It has a rotor and a stator. The rotor is the thing that moves. The stator is the thing that's stationary. And in a brushless DC motor, the stator is electromagnets, right? And so in my motors here, we have 20 or so electromagnets. And what are we moving, though? How do we move something? What we actually move is a permanent magnet. So a permanent magnet is, as opposed to an electromagnet, just something that you got out of the ground that happened to be magnetic. So there are lots of things like this, like your fridge magnets at home. These are usually neodymium magnets, which are very strong. I have a couple of those at home, and they're really hard to pull apart. And what we do here is actually something really creative. So remember that magnets can attract and repel each other. So what we're going to do is actually use these electromagnets in the stators of the motor to attract and repel this magnet in such a way that we eventually spin the motor. So you can see it in this diagram here, where, and remember, opposites repel in the magnet. And so what we're going to do is, we're going to pull. Here we can see that we have a north and south pole in our magnet. We want the south pole to be attracted by the north pole will be repelled by the south pole. And what we can do is actually turn these magnets on and off creatively to actually spin that internal magnet in the rotor. And ultimately, this will generate thrust for us. This will actually rotate the motor, will generate thrust by the Bernoulli effect. Very, very nice. This is very simple, very fundamental. And this is how these UAVs eventually get off the ground. So one problem, we have to power these, right? They actually have to be able to turn on and off. and they have to be able to turn on and off very quickly. So how do we power them? Well, we power them with batteries. So I have a battery, a lithium polymer battery right in front of me. This is routed to these motors via our flight controller, power distribution board, and also electronic speed controllers. So these things, electronic speed controllers, what they do is they actually determine, or they're told to determine, how often we switch on and off these electromagnets so that we can spin the rotors. That is their only job, very, very simple. But they take power from the battery, and they send it to the motors, and they eventually spin the rotors that allow us to fly. Now, we bridge the gap between these two things with our flight controller. This is just a little onboard computer. You can actually see the orange cube right up there. And most of the time, what this is doing is determining which speeds each rotor should spin at. All that it's doing is just trying to balance the UAV and move it in a specific direction. So if we want it to move forward, this flight controller is determining which rotors are spinning at which speeds to move the UAV forward as fast as we want it to move. If we want it to fly up, that's what it's doing. If we want to fly 30 degrees up and to the left, that's what the flight controller is doing. Very, very simple. All these components, they might look complicated, but really that's all they're doing. We're spinning things. We're telling things how fast we want them to spin, and we're balancing the rotors with our electronic speed controllers by actually telling these coils how fast they should rotate, so we figure out how fast a rotor should spin. Very, very simple. They might look tough, but really that's all they are. Now, that's basically a drone. That's almost all you need to make a drone. So if you have those components, you're pretty much good. But we can't just fly them all loose, right? We can't just have a bunch of wires flying up in the air. We need some rigid airframe to actually have our drones be able to move and keep all their pieces together. So you can see the airframes here that I have. They're usually made out of carbon fiber because we want our UAVs to be very light. We want them to be as light as possible because this takes a lot of energy to get things up in the air. And so we have these carbon fiber airframes that we connect all of these components to. Now, you can see that we have a bunch of different configurations that we can, with the various rotors that we have to attach them to the airframes. I have a very small drone over there that's a quad rotor. It only needs, it only has 4 rotors, and that's totally fine. I would say most of the UAVs you would buy, if you went to Best Buy, you'd have a quad rotor UAV. I have 2 hexacopters here, so they have 6 rotors. We can go up to 8 rotors, 10 rotors, et cetera, et cetera. This is just a matter of 1, stability, and 2, thrust. The more motors you have, the faster you can thrust, the more stability you can have. That's really all it is. Nothing more complicated than that, but usually bigger drones will have more rotors. Now, I mentioned the flight controller, and I said basically all it's doing is trying to push the drone in a specific direction. And what it's doing is actually sending commands to these electronic speed controllers to, as I said before, determine the rate at which those stator magnets are turning on and off, right? Very, very simple. But what it's trying to do, as I mentioned, is to balance the UAV in such a way that it's actually moving towards some goal. So here we see a video of a UAV that's very carefully balancing a glass of water. That's basically what we're trying to do, right? We're trying to create thrust in such a way that we move in the direction that we please. In this case, we want to remain stationary. That's all the flight controller is doing. Now, I mentioned telemetry as well. So like I said, telemetry is just sending data from point A to point B over the air. And we have a lot of different ways that we can use this telemetry to control our drone. So most of the time, if you buy a drone somewhere, like at Best Buy, you'll get a controller. Or you can use an app on your phone. And you can use a controller like this. So this is one of our Radio Master controllers that you can see to just fly the drone. So if you pull up on this stick, the drone will fly up. If you use this stick, you can push it forward and backward. You can spin it around. And we transmit those control commands over the air the same way that you would listen to the radio or use your Wi-Fi. Different spectrum, but same concept. And that's how we send data to our drone, or in that way. We can also control our drones using GPS. So I'll mention this later, but you can send GPS waypoints, these are latitude and longitude coordinates, to your drone and have your drone fly to those coordinates, right? Pretty magical, but it's actually really simple. It's just a little PID controller, which if you go to engineering school, you'll learn about. Very, very fundamental. But we can use GPS satellites to actually control our drones, and we can also just use our computers. So I usually will use my laptop. This is actually a picture of me somewhere in a cornfield controlling a drone with my laptop. But this is most of the time what we do. We want a little bit of extra computation, so we control our drones that way, usually via Wi-Fi or by plugging into a controller. Now, the most important, and at least to me, aspect of the UAVs are these cameras. So these cameras are really what are going to facilitate these interesting applications that I'm going to talk about later. And the idea is that these cameras are incredibly powerful, right? They allow us to capture these visual representations of our environment, of our natural world. And we can use things like a regular RGB camera, right? Your phone camera or this Canon EOS camera that's relatively high quality. And we can use that to capture these conventional RGB images. And when I say RGB, what I mean is red, green, and blue. So if you ever gotten way too close to your TV or your computer monitor, you'll know that those monitors are actually displaying things not in the actual color that you're seeing, but in combinations of red, green, and blue, very creatively. That's how all images, or most images, are formatted. And we can send these kinds of cameras up into the air and get very nice pictures, right? We can get pictures of our cornfields. We can get pictures of forests, pictures of lakes. And these are all very useful to us. But sometimes we need other kinds of sensors. So we can use things like thermal imaging. Thermal imaging senses black body radiation. It'll tell us, based on that radiation, how hot something is, or it'll give us a good estimate. So you can see, say, in a crop field, if crops are diseased based on the thermal signatures they give off. You can also say, if you're looking at a forest fire, where that fire is. And oftentimes, with forest fires, those fires are smoldering below the tree canopy in ways that you can't really see with a regular RGB image. So we can see deeper into our environment with different kinds of sensors. One other kind of sensor that I've been working with recently is this hyperspectral camera. So light is not static, right? There are different wavelengths of light that represent different colors. And if we can strain ourselves to just red, green, and blue, then we're leaving information on the table. Hyperspectral cameras capture data cubes. So these are hundreds of different spectra of light, all in one image, all the way from infrared to ultraviolet and everything in between. You're capturing blue, green, red, different types of those colors. And we're combining them into this data cube that we can then map to spectral signatures of underlying materials. So we can find different metals. We can find different problems in crop fields that give off certain spectral signatures. This data is very hard to process, but we can put these on board UAVs and get some really interesting insights. So we've got all these sensors. We've got these motors. We've got these flight controllers. We also need some onboard computation. Now, UAVs can't just fly this laptop or a big desktop computer or a big server. We need to be very careful about what we instrument on board these UAVs. So under this UAV, actually, we have a very interesting piece of technology. We have one of these devices. It's called an NVIDIA Jayson. It's an embedded GPU. It's really just a specialized device for doing really highly parallel processing. We have one of those on board our UAVs. We can also use things like FPGAs. If you don't know what that is, the field programmable gate array. That might not have helped explaining what it is, but just think about them as very configurable computers that you can put really specific lithographies on without actually having to burn them onto a physical chip. We can also use things like TPUs. These are really new technology, very, very lightweight for matrix multiplication, which is very fundamental to artificial intelligence. So we usually use very exotic compute platforms as opposed to what you're used to seeing maybe in your house or at Best Buy. Now, with that said, that's basically what these drones are and more or less how we instrument them to at least facilitate this intelligence. But I want to talk a little bit about what artificial intelligence is. And I want to talk about this because it's so fundamental to these interesting applications that we can deploy on these UAVs. We need them to be as smart as possible. So to begin, I want to talk about how UAVs are piloted. And I'm just going to talk about this very briefly because in truth, it's extremely complicated, the stuff I'm going to get into. So I'm going to try to keep it at a high level. But UAVs are usually piloted by people, right? Most of the time, if you see a drone flying, somebody's got a controller in their hand, right? And that's very good. That's a normal thing because people tend to be actually very good at flying these, particularly the people with licenses who do this for money. They end up being very highly skilled, and they're able to learn and adapt to scenarios, right? If bad weather blows in, this pilot's probably not going to allow the drone to get blown into a tree or blown into traffic or blown into a medical helicopter or something terrible, right? This person's going to be able to adapt to that situation. If we were automating the drone, we have to consider that scenario. The problem is that people get distracted. They have to eat and sleep. by regulatory standards, we can't have one person operating multiple UAVs, so that makes certain swarming experiments very hard to run. So it's not ideal to have people piloting these if we want them to be pervasive all over the place, solving really big problems, but it's good for now. Now, we also have this software automation that we can use. So these are, say, dropping latitude and longitude coordinates that we can put into our software to allow our UAVs to fly based on those coordinates. We can have them go from point A to point B to point C to point D. Problem with that is that this isn't really very extensible, right? It's consistent, it's inexpensive, but it's very limited in adaptability. If my UAV senses something that it doesn't like, it can't really change its mission. The mission is fixed. And so what we do is software autonomy. We actually use the sensor data that we pick up from our UAVs to determine where those UAVs will fly. And this can impart human-level skill into the UAVs. We can actually make them better at piloting themselves than humans are, and it's relatively inexpensive as long as you do all the research and development. The problem is that this is pretty difficult to build. It's not so simple to actually make happen. So from here, I want to start talking about how we actually do this. And I'm going to start by talking about artificial intelligence. So you all have probably heard the term AI in the news, on social media, from your friends, and you might not really understand what AI is, right? You might think, oh, AI is just, we made computers smarter. But how do we actually do that, and how has it evolved over the years? Now, when I think about AI, I think about the original implementations of AI, which are solvers for old games. So if you take a computer science class, you might hear that some of the first AI implementations were actually things like solving checkers. Checkers, if you're not familiar, is a game that is completely solved. That means that if you know how to play checkers super duper well, usually beyond the capabilities of a human, that it is always winnable if you start first. Now, we can make an algorithm that will beat a person at checkers every single time, but it's very hard for a human to do that. So this is why we call this type of thing artificial intelligence. It's beyond a human level of intelligence, or is intelligence that's working in a way that is non-obvious. Now, we have things like modern chatbots like ChatGPT that are much beyond just beating people at checkers, right? I can ask ChatGPT to write me a chocolate chip cookie recipe in the style of Homer Simpson, and it'll do that for me, right? Is that benefiting society? I'm not so sure. But it's a really interesting technology, right? And it's very hard to figure out how you would do that, right? How would you actually make that happen if you wanted to design that yourself? Very tough. What we're going to talk about today is computer vision. So computer vision is this idea that we can make computers see things, right? And if we're going to use our drone's cameras to do interesting things, then we're going to have to make them determine or tell us what's in their environment. So you see this image of these cats. We can actually figure out with a little bit of computer vision if where cats are in an image, and if they're eating, or if they're like my cat's not eating, then there's probably something wrong. So how do we actually use this kind of stuff in the UAV space? Well, we use computer vision for all sorts of things. We use it for control. So this is actually sending those commands to the motors to tell them how fast to move. We use it for planning. So planning is figuring out where we want our UAVs to move. This is actually us flying one of our UAVs on the courtyard and doing some real-time localization and mapping, which I'll talk about in a second. And we also use them for object detection, like finding this invasive spotted lanternfly. So I'm going to talk a little bit about planning, just very high level about planning. And then I'm going to talk about object detection, because I think it's very interesting. And then we'll talk about how we can use these things in the real world. So first, one very important task, if we're trying to automate or allow for autonomy in the UAV space, is actually figure out, on board our UAVs, one, where they are in their environment, and two, how they can fly without crashing, right? So if I'm a UAV, or if I'm just a human, most of the time what I want to know is, where am I, and how can I get around to where I want to be safely? Now, we need to do this on board our UAVs in a way that, again, is computationally efficient and doesn't cause accidents like this. So how do we do this? Well, the very broad term is something called simultaneous localization and mapping. The idea is that our UAVs actually navigate their environments very similarly to the way that we do. We allow our UAVs to find landmarks. So if you see this image up here, we have the cathedral at Notre Dame. This is a very common world landmark. I'm sure a lot of you recognized it. And if somebody dropped you in the middle of the Ile de Cité in Paris and you saw the Notre Dame, maybe you would recognize it. But one very important thing about human cognition is that if you see this building or your house or a street sign, and then you move a little bit to the left and back, you'll still know that it's a street sign even though it's in a little bit different orientation, right? And so in this image, we can see that we have two different views of this cathedral, and despite the fact that it looks a little bit different in those two views, we know it's still the same cathedral, right? Humans know that, but it's very hard to get a robot to know that. It's very difficult. So what we actually have to do is something similar to what humans do. And you'll see this a lot in artificial intelligence, that really we're trying to emulate human cognition. And the idea here is that we want to find features. We want to actually find different aspects of this image that look the same, even if we move a little bit to the left or move a little bit to the right or go a little bit higher or move a little bit back, right? We call these features. And usually these features, again, will look the same or look very similar no matter how we move. They're rotation, translation, and scale invariant, as we call it in this space. And what that allows us to do is something like this, where we can build a depth map, which is actually using multiple cameras to build an image that describes how far away different pixels are instead of just what they contain. We can use that in conjunction with features to actually figure out and map our environment. So we can build this three-dimensional map, and we can use that three-dimensional map to navigate the environment without hitting anything. It's very, very nice. It's definitely difficult to understand, difficult to process, but this is a capability that we have and something that we can run, actually, particularly on this UAV. Now, that helps, right? It's nice. But if we want to do something real, if we want to actually solve a real problem, obviously we can't crash, but we need to do something a little bit more complicated, right? We need to be able to recognize things. We need to be able to figure out if this lake has some problem with it, if this forest is on fire. So how do we do that? Like I said, we use computer vision, but the subsection of computer vision that we're going to explore here is something called object detection. And what we're trying to do here is figure out not just if there is some object in our environment, but what it actually is. Is it a spotted lanternfly, or is it a cicada? Is it a healthy leaf, or is it a leaf that's got defoliation that we want to avoid? Is it a nice clean lake, or is it a really scummy, disgusting lake that we should help clean up? So we need to figure out how to detect these things just from an image with a computer. Very, very complicated, but I'm going to try to break it down here. So the fundamental question is, can we design an algorithm, right, a term that we probably hear a lot, to determine if an image contains a specific object? Now, you might not know what an algorithm is, so I want to go over this because this is a very important term. An algorithm is just a set of steps, consistent steps to transform an input into an expected output. That is all an algorithm is. When you hear that word, that's all that's happening. It's not, no one's trying to be confusing. That's just what's going on. Now, you probably all use algorithms every day, right? You might not even know it. Every time you wake up, maybe you have a series of steps that you follow, right? I don't know about you guys, but I look at my phone for about 5 minutes. Then I get up and take a shower, and I brush my teeth and whatnot. But we all know how to cook, right? Or most people know how to cook. And so one good example of an algorithm is a recipe, right? And so we take these inputs, maybe eggs, butter, milk, et cetera, and we can follow a recipe to then create an expected output. And that output might be scrambled eggs, it might be an omelet, it might be something else, but all we're doing is following steps here. And so what we want to do is come up with a series of steps that we can use to tell if an image has a specific object in it, right? Does this image contain a bird? Does it contain a cat? Does it contain a dog? Does it contain anything, right? That's pretty hard. It's very hard to do. And so I'm going to illustrate why this is hard using just a few examples. So what we're going to do here is we're going to look at a few images of cats and dogs, and we're going to see if we can tell if those images contain cats or dogs and why. Really what I want you to think about is, why is it a cat? Why is it a dog? Why is it something else? So if we look at this image, this is one of my cats. We can see that this is clearly a cat, right? You as a human being know this is a cat. But why is it a cat, really? What makes it a cat, fundamentally, right? It has two pointy ears. It's got these nice round eyes. It's got this cat-like mouth. But fundamentally, what makes this a cat, right? How do we actually tell this is a cat mathematically? It's very, very difficult or impossible to do without some sort of statistical process. But we know it's a cat, right? Similarly, you have an image of a dog, right? It's clearly a dog. It's still got two pointy ears. It's got a long snout. It's got this tongue. It's got this beautiful coat. But how do we know this is a dog? How do we know this is different from this cat, right? How do we classify them into two different things, right? Maybe if we think about the differences between these two animals, we can see that this dog has a black and white coat and this cat has a beige coat. Is that the difference between a cat and a dog? You and I both know that's not true, but a computer is going to have a really hard time telling that, right? And so if we show our computer this cat, which has a black and white coat, maybe it'll think it's a dog, right? It doesn't have any understanding of why this is a cat and why another image, like this one, is a dog. So what we have to do is train our computer to do this. We have to actually teach it like we would teach a human. And not only is that difficult with just these two things, but what if we start incorporating other things, right? Is this a dog or a cat? It's a fox, right? It's something totally different. So how do we tell our computer that this isn't a dog or a cat, right? This gets very complicated, right? And not only is it complicated because there are other animals, but we have animals at different positions, right? So this isn't just a head-on picture of a cat. It's a cat doing something weird, right? It's yawning. How do we know this is a cat? Very, very difficult, right? And we also have completely other objects, right? This is just a chinchilla. How do we know what this is, right? We have to train our computer. We have to do the exact same thing that people do. We also have to avoid things that are totally irrelevant, right? Like this F-150. So how do we do this? How do we actually train a computer to detect dogs versus cats, or spotted lanternflies versus cicadas, or disgusting lakes versus clean lakes, right? How do we do this? So if we can't use a classical algorithm to do this, what we actually have to do is think about how we know what cats are, right? How did you learn what a cat was? So for me, this is a picture of me when I was a kid. I know what a cat is because I had cats growing up, right? I had people show me cats. I touch cats. I like cats. So I figured out what cats were by experience, right? So can we create an algorithm that will learn from experience? And that's what we're going to do here. So we're going to, instead of just mathematically defining cats, we're going to teach our computer what a cat is. So the way that we know what cats are, the way that we recognize things is through our neurons in our brain, right? Very complicated concept, but basically we have a bunch of these neurons that link together and fire when we see certain patterns. So can we teach our computer to recognize patterns? And the answer is yes. We can use artificial neurons, mathematical neurons, to do this. Now, I will say this is very complicated, so I'm going to gloss over this very quickly. But the general idea is still the same as a regular algorithm. We want to take an input, and we want to process that input and turn it into an output, right? And so for this picture of my cat, I want an algorithm to tell me that this is a cat and not a dog. Very simple. So how do we do that? This really complicated image. Don't worry too much about this, but the idea is that we're going to take this image and we're going to deconstruct it into its constituent pixels, right? Images are just groups of pixels. We're going to pass all these pixels into our, we call a neural network, very similar to how neurons work in our brain. And each one of these little neurons, these machine neurons, has a value in it, a decimal value between 0 and 1. And what we're going to do is multiply the pixel values in this image by these decimal values. And eventually, we're going to add them all up and see what the ultimate resulting value is. Usually, we want to constrain it between 0 and 1. So if the value is greater than 0.5, it's a cat. If it's less than 0.5, it's a dog, right? Problem is, when we create these things and we don't train them, they're pretty dumb. They don't actually know what cats or dogs are. They're basically just guessing. And so what we want to do is train them. And how we do that is we take thousands of images of these cats and these dogs, and we continually, over and over and over again, train these algorithms. We reinforce them. We say, this is a cat, this is a dog. And what we actually want to do is update the internal floating point values in the neural network. We want to tell the neural network, particularly if this neuron right here is causing the problem, we want to update it so that it changes its result. Ultimately, it reinforces that, hey, this feature that I'm seeing, I know that I'm wrong about it. I'm going to update a little bit in a direction that points to the correct answer. If I'm saying that this image is a dog, I want to update a little bit to say that I'm a cat. Very, very simple version of this. But ultimately, we train these algorithms. So if they do poorly, we recalibrate our weights, and we try again. And ultimately, they do good enough that we can deploy them on board our drones. So I know a very high-level explanation, but this is the basic idea, that we have to train these algorithms so they ultimately can recognize the phenomena that we want to detect. So what we do is we put these on board our drones, on board the onboard computers that we have. And what we do with these is we take the camera feeds from our drones, and we pass the images from the camera feeds to these algorithms, these artificial neural networks, and ultimately use them to detect phenomena that are of interest to us, like this invasive spotted lanternfly or crop diseases or anything that we're trying to detect to meet our goal, to facilitate our application, right? So with that out of the way, we're done with the complicated stuff. Now we can talk about the cool stuff. How can we actually use these to benefit us? What is this? How do we put this all together in a way that's relevant, in a way that helps society? So I'm going to talk about 3 applications that my lab has worked on or that I've worked on in the past that I think really demonstrate how we can use UAVs for good. So one is in agriculture. We're going to talk about how we can use UAV swarms to monitor crop diseases in fields. We'll also talk about an application in ecology. This is currently ongoing where we're using these interesting hyperspectral cameras to determine if lakes are healthy or unhealthy. And we're also going to talk about something in ecology and agriculture, where we're trying to detect the invasive spotted lanternfly, my nemesis, which is really harming the agricultural industry, particularly the grape industry in New York. So first, it's important to remember that, of course, agriculture is fundamental. It fulfills one of our fundamental needs. Everybody in this room has eaten something today that came out of a crop field, I hope. The problem is, though, that with climate change and with our increasing population, agriculture is in this downward spiral, right? We're experiencing this negative feedback loop where we're still, our population's growing. We expect to top out around 11 billion people in about 50 years. But as we can, continue growing as a population, we need to feed more people, despite the fact that climate change is making agriculture harder every day, right? So we're losing arable land in the places where people farm. We have stronger storms. We have more wildfires. So how do we defeat this negative feedback loop? How do we close the so-called yield gap, this gap where every crop that we plant doesn't always grow into something that we can eat? So the way that we've solved this challenge in the past or approached it is through so-called agricultural revolutions, right? So humanity started farming in 10,000 BC, and we started using things like irrigation to get water to crops so they could grow in arid lands. And this was how agriculture worked for about 10,000-ish years. Now, in the 18th century, we started thinking about agriculture a little bit more scientifically. How do we actually rotate crops so that we can re-impart nitrogen into the soil to make our crops grow a little bit better? And then in the 1940s, when we figured out how to make nitrogen fertilizer, we started using that to make agriculture even more prosperous. And this is actually one of the principal reasons that our global population is so high now, that we can actually feed everybody, right? It's very nice. Now, in our literature, we're talking about agriculture 4.0. So these are applications of things like drones or factory farming or genetically modified organisms to try to make agriculture more robust to things like climate change. And I'm going to specifically talk about one area of agriculture called digital agriculture. So this is the application of modern sensors like our UAVs to agricultural problems. And what we do here is we take a crop field that's been growing or that is somewhere in the growth cycle, and we instrument it with sensors, right? So we can have a sensor for something like soil or moisture. We can check the pH of the soil, which is instrumental to crop growth. And we can use our UAVs to monitor that crop growth from the air to sense the yield, or to estimate the yield of the crops. And we can use this to build maps that we can ultimately then funnel into treatment strategies. So we can actually cut off any of these negative agricultural impacts using these technologies, right? We can determine, is there a disease in our crop field? Is there some, are we underwatering? Do we need more pesticides? Do we need more herbicides? And we can do this in a way that's sustainable, right? Where we're not just dumping chemicals onto our crop fields like we were in the 70s, where we're doing this in a way that is so-called variable rate, that is happening as the crop field is growing and in a way that is more sustainable. So how do we do this? Well, actually, the way that our autonomous drones navigate crop fields is very similar to how farmers navigate their fields. So if you know a farmer, if you are a farmer, you'll understand that there are so many problems that your crop field can have, right? There are hundreds of diseases for any given crop, and you can experience any one of them any given year. Usually the local agricultural extension will put out their list of things that might happen in the area, but anything from drought to defoliation to large storms to diseases like scorch and mildew, or to beetles, to just environmental factors in your field like harvest ruts can impact negatively or positively your crop field. And so what we want our UAVs to do is actually figure out where problems are occurring and then identify those problems so we can design treatment strategies. So what we do is we learn the crop field like a farmer would, right? Where farmers will know where the harvest ruts are. They'll know the topology of the field. They'll know, where the dirt is, fertile and where it's not doing so well. And we want to actually, from there, detect phenomena. We want to find beetles. We want to find mold. We want to find, and we do this with all with machine learning, right? We use those neural networks that I talked about earlier, and then we produce maps, right? We map the field so that we identify these problems and either tell our drones or tell the farmers where they are, and then we apply treatment. So one example of this, something that I worked on, this was in 2021, was solving this problem for soybeans. So soybeans are a very high impact crop. We produce about $50 billion worth of soybeans every year. I'm originally from Ohio, and if you drive through Ohio this time of year, there's soybeans everywhere. But they're very important. They're a very big agricultural export. And really, soybeans are pretty greatly affected by something called defoliation. So defoliation is this idea that these leaves are losing their matter. They're losing their leaf area. And they do this naturally. They defoliate over time in the field, but if they defoliate early because of beetles or because of mold or some other disease, then what happens, right? These leaves are vital to photosynthesis. We are turning light and carbon into plant matter, into yield. And so we're doing this only by the grace of this leaf area. So if we lose leaf area, we're ultimately going to have lower yield. So we want to mitigate this. We don't want this to be a problem in our crop fields. And to make it less of a problem, we need to first detect it, or detect what's causing this defoliation. Oftentimes it's beetles. Oftentimes it's stink bugs, really. But in this case, we were detecting Japanese beetles and their leaf defoliation because that was what was affecting our state at the time. So how do we do this? Well, bring back this diagram. We have to get thousands, it's actually tens of thousands, of defoliated and non-defoliated images of our crop fields. And we have to train these neural networks, right? We train them until they're very good at detecting this defoliation. And then what we can do is we can deploy them on board swarms of drones. Very simple, right? So we just use all these things that I discussed earlier that we already know about, and we can put them together in a way that actually helps us map these fields. And so we did this. I did this in 2021. I spent about 6 weeks out in a soybean field in Ohio. I actually have a video of this a little bit. I'll skip through it a little bit, but so we can see the drones flying. But we had to set up a series of computers and drones for our swarm out in this field in Ohio. We've got all these remote controllers that we have. We were controlling them using actually tablets connected to these remote controllers. But the basic idea is just as we've discussed, right? That we take these drones, instrument them with machine learning, and we actually allow them to go out, fly through the field, and build these maps, right? And so they're able to go and fly totally by themselves. They're not, I was not controlling these besides clicking a button. They just go out, they fly, they map their areas of the field, and we build these very interesting maps, right? It's very nice. And we can use this fundamental design for a lot of different things. We can do a lot of really cool things with this. So the next thing that we've worked on, something that's ongoing, is something in ecology. So ecology is just the study of our ecosystem, right? Ecosystems are very vital. And what we can do is actually detect things like these harmful algal blooms or wildfires or oil spills or even impact from hurricanes. And all of these things impact not just billions, not just trillions, but quadrillions of animals every year. And what we can do is use UAVs to sense and potentially mitigate some of these serious problems. So up here is a picture, and this is a real picture from Lake Erie in 2014. Sometimes very important lakes get like this. They look scummy and disgusting like this. And not only is this disgusting, it's unpleasant to swim in. That's not super important, right? We don't all have to swim in Lake Erie every summer. But this is harmful to the plant life, to the aquatic life in Lake Erie. It hurts fishing. It hurts our waterways. It hurts drinking water supplies. And this was actually a very big piece of news in Ohio when I was in Ohio in 2014, because the whole city of Toledo was basically on a boil order for their water. You couldn't drink water in the city of Toledo for multiple days because the water was so disgusting and full of cyanobacteria, which is toxic to human health. So, can we use our UAVs to predict algal blooms? Not just to identify them, right? Because you can identify an algal bloom yourself. You go down to Lake Erie and you see if it's green, right? But what we want to do is figure out if Lake Erie is going to be green, not tomorrow, but next week or next month. Can we figure out from just a regular normal looking lake if there are the environmental conditions present to turn our lake into something like that, right? To take the normal Lake Erie and turn it into a harmful algal bloom. So what is a harmful algal bloom really quickly? It's just when algae, particularly algae that has cyanobacteria or cyanotoxin in it, turns into or becomes significant enough in the lake that it blooms in a way that looks green and disgusting. So this happens naturally. Actually, I drove by a couple ponds on my way here that definitely had algal blooms in them. So it's a natural part of particularly very small bodies of water. But when it happens in a large lake like Lake Erie, usually it's because of runoff from agriculture or sewage, things that contain a lot of nitrogen that allow these algae to grow in mass, right? It's like an opportunistic infection in your body. So what we want to do is find out if these lakes are going to be susceptible to this problem. And why is that? What does it matter if we can figure out if they're susceptible? Well, there are a lot of things that we can do to actually prevent harmful algal blooms if we know they're going to happen. One way that we can deal with them is we can actually spread clay all throughout the lake. You can take little fine particles of clay, drop them in the lake. There's all sorts of clay at the bottom of the lake anyway. It's not harmful to the ecosystem. But what it'll do is it'll take that algae on the top of the lake and it'll sink it down, right? And algae needs oxygen and it needs light to photosynthesize. And if we sink it down to the bottom of the lake where there's no light, then it's not going to cause an algal bloom. So we can do that. We can also limit agricultural runoff. We see that's going to be a problem. We can close beaches, et cetera. So how do we detect these things, though? How do we actually figure out if the lake is going to be green in 4 weeks if we can't see that it's green today, right? Now, what we actually do is use our UAVs, again, to get very, very close up to the lake and detect with hyperspectral cameras this harmful algal bloom or this cyanobacteria. So one important thing to note is that oftentimes with this field called remote sensing, where we're trying to take pictures of things from far away, we can use satellites or we can use helicopters, but drones provide this very nice benefit. They're highly maneuverable, they can collaborate, but they can get really close, right? Instead of a satellite that's thousands of miles away or a helicopter that's thousands of feet in the air, our UAVs can get up close and personal and get these really high quality images. And so this is very important for hyperspectral cameras. So hyperspectral cameras, like I said, they capture tons of different kinds of light. And that can be very nice for us. We can actually use all of those different wavelengths of light to identify materials that we couldn't see with just a regular RGB camera. So down in the bottom right corner, you can actually see an example where a team in Germany was able to identify somebody who was wearing camouflage in a field just by their hyperspectral signature. You can't actually see it in the RGB image, but in this plotted hyperspectral image, you can clearly see that there's an anomaly in the field. And we can use this exact same concept to identify harmful algal blooms that we can't see in regular RGB images or with just our eyes. So why is this important? Or sorry, how do we do this? Well, one important aspect as well with our UAVs is that we need to get very close to the lakes to detect harmful algal blooms because these images have to be very high resolution. So hyperspectral cameras are necessarily considerably lower resolution than regular RGB cameras because they take more semiconductors to actually construct the pixels. So if I wanted to, say, have a 1080p hyperspectral camera, it would take over 150 times as many semiconductor or as much semiconductor mass in the camera to actually do that. Actually a little bit more than that because there's some other apparatuses you have to have. But hyperspectral cameras capture data at very low resolution, right? And so we want to get very close. So this is actually an overlay of our UAV data and satellite data from Landsat, which is a satellite that scientists use. And you can see that these Landsat hyperspectral pixels are like 80 meters across, right? That doesn't provide us enough information to actually make a decision about whether or not this lake is healthy. So we need to get up close and personal. We need a UAV. We need something that's maneuverable to get into this lake. So what we actually do is identify spectral signatures in the lake from this lake water, right? From just very normal looking water that can give us hints as to whether or not we're going to have an algal bloom a few weeks later. And really what we're looking for is this very specific red pigment that cyanobacteria gives off. This doesn't look very red, does it? probably shouldn't, right? But there is a little bit of red that cyanobacteria gives off that's not normally present in water. And what we can do is detect that even before the water looks like this, it looks disgusting and green. We can see that red signature, and we can know that there's cyanobacteria in our lake. And all we have to do is fly our UAV over this. Now, the stuff I'm leaving out, we have to process tons and tons of data in real time. But we can do this to find algal blooms very, very quickly in situations where the water looks particularly normal. So this is something that, this is actually a project that's been going on for a long time at BU. This was actually before me. And I've sort of inherited the drone component of this, and it's a very interesting project. But it's mostly focused on Lake Chautauqua, where we go out and actually scout with our UAVs and in boats and collect water samples. Very interesting project, and really fun to work on. And it's also really fun to work with these cameras. They're very, very interesting. Now, the last thing I wanted to talk about is something that's very near and dear to my heart. And this is the spotted lanternfly. So has anybody here heard of the spotted lanternfly? Does anybody know what this is? Oh, thank God. OK. All right. So this is great. I'm really, really worried about this. So the spotted lanternfly is an invasive insect. It's come into the United States from Southeast Asia, I believe China and Vietnam. I don't know if we're actually sure which country, but really, they're not a big problem there, right? They have natural predators. They're part of the ecosystem, but they came over here, and they are flourishing. They don't have very many natural predators. They have a couple natural predators, but not in significant enough numbers. And so they spread really fast. They spread all over the place. If you were in New York City last August or September, they were all over the place. They're swarming buildings. And they're gross and they smell bad, but that's not the actual issue here. That's, we shouldn't judge spotted lanternflies for being a little bit smelly. The problem is that they harm agriculture, right? They are very, very bad for grapes. And what they do is they like to eat the grapes and the grapevines, but they leave behind these substances. It's called honeydew. It's a very stinky substance. But it allows these grapes to get moldy. We end up losing entire grapevines or vineyards to the spotted lanternfly. So once these things get into grapes, get into grapevines, get into some other crops, they're completely lost. It's terrible. Now, I don't know if you know this, but New York is actually the third largest grape-producing state in the country. It's a distant third behind California and Washington. But our grape industry is relatively prominent, right? We want to allow this to prosper, and we want to find a way to deal with this and other invasive species that are only going to increase as we continue our global connectedness and as we continue with climate change, as our climate changes a little bit more and more. So what we're trying to do is put all of the stuff I talked about together to allow us to identify these spotted lanternflies in the dense forests that they often inhabit. So what we're doing is actually building data sets of spotted lanternfly images. And what we're doing is, I think that it might be fair to say that we definitely have one of the largest labeled data sets of spotted lanternflies at the moment. And we're continuing to label this data set so we can build these machine learning models to detect spotted lanternflies. Now we're trying to make these models really light and small so we can run them on board UAVs as fast as possible. But we need to allow our UAVs to navigate these dense, deep, dark forests. Because what we're trying to do is not find the bugs themselves, but find their eggs. So their eggs stay in these forests for about 6 months. They sit high up in tree canopies. And what we're trying to do is identify those egg masses with UAVs at a much higher accuracy and much easier than forest workers or extension educators or people that work in the Department of Agriculture would be able to do. And ultimately, what we're trying to do is prevent the spread of the spotted lanternfly, the projected spread of the spotted lanternfly, all the way out to the western United States. That's what we're trying to do. And so this is one of our main research projects at the moment. Very, very interesting. So we're collecting tons of data on this. I've got actually students in the audience who are developing the simultaneous localization and mapping that we need to navigate these forests. And we've got deployments that we're working on, particularly at the Blue Marsh Lake, which is infested with spotted lanternflies. It's in Pennsylvania. They're a very big problem in Pennsylvania. But there's hope, right? Hopefully we can use these interesting technologies that I've discussed to try to stop this problem, to try to stop the spread of the spotted lanternfly. And I think we can get there. Now, that's about the end of the talk. I hope you learned a little bit about drones, about autonomous systems, and really what I want to leave you with is that I think the future for autonomous robotics is relatively bright, right? We can use these things for bad. We can use them for neutral. We can make movies and we can make light shows. But with a little bit of know-how and a little bit of hard work, we can make them do some really interesting stuff. And so I think that ultimately we can use autonomous systems to automate things like farming or treatment for invasive species or other ecological workloads. And I really do think that with a little bit of education, with a little bit of help, a little bit of money, a lot of this stuff can really help us feed our growing population, can help us mitigate some of these serious effects of climate change. So thank you very much for listening to me. I really appreciate it, and I really appreciate you letting me come here. My name, again, is Jayson Boubin. I'm a professor at Binghamton University. And if you have any questions or you just want to look at my drones, feel free to come on up, and I'm happy to answer.
Actually, I was going to say we have a number of people on the live stream, and so I've just sort of changed over to a camera section. So maybe you could walk over and do a quick explanation of what we have here.
Yeah, absolutely. So these two drones, these are actually from the applications that we're working on. So this is the drone that we use for hyperspectral processing. Right here is a hyperspectral camera. This is from Corning. So Corning, a lot of people don't know this. Corning has really good, they do a lot of research into optics, not just glass, right? And glass is very important for optics, for cameras and whatnot. So this is a Corning hyperspectral camera that's specifically designed for UAVs. It's actually a lot more expensive than the drone it's on, right? It might not look very impressive, but it's incredibly impressive internally. So this is our drone that we use for that project. This is a DJI Matrix 600. It's a relatively older model, but it still gets the job done, and really, really helpful for that project. The one that we have over here, this is an Aurelia X6 Max. This is a US-made drone, and this is the one that we're mostly focusing on real-time simultaneous localization and mapping, and for that spotted lanternfly project. So you can actually see here we have, instead of a regular camera, like you might have at your house or on your phone, we have a stereoscopic camera. So we actually have two cameras in one. You can kind of see they look like eyes. But what this camera lets us do is build depth maps. So we can use the concept of parallax, which is very important for astronomy, to actually figure out how far away pixels are from each other in an image just by moving a little bit, right? Very nice, and having these two cameras move with our UAV. So this is really, really helpful for that simultaneous localization and mapping, and we even have a little payload down here for that simultaneous localization and mapping workload. Here we have, this is just a small drone that I have, a Parrot Anafi. This is something that you might pick up at Best Buy or have at home, but we like to use these for small experiments. We want to go fly something out. We don't want to get all sorts of approvals like flying one of these big drones. We can take these small ones and we can make them run in swarms very easily. It's a little bit harder to get the big ones up in the air. And of course, I always love to show these off, these lithium polymer batteries. If you want to come up and feel this, it weighs about, I think it's 1.5 kilograms or 1.2 kilograms. These are huge batteries. I have 4 of these batteries in here. It takes 2 to fly this drone for about 30 minutes. And that's 30 minutes on a nice, clear day. So one very big challenge for us in the UAV space is actually maintaining enough power to keep our drones in the air for long enough time, right? This is a huge fundamental problem in this space because flight is so inefficient, or the specific type of flight that these UAVs use with their electromagnetic motors, incredibly inefficient for lifting the payloads they lift. So we can really only fly for about a half hour, even with a bunch of batteries on board. So just a little showcase of the technology we have here today. And again, if you have any questions, just let me know. I'm all ears.
All right, if you do have any questions here in the audience, just raise your hand and we'll get you on the microphone. All right, here we go.
Hey, Jayson, great talk. So my question is, for that soybean project, how did you guys get the initial data set to do the training?
So that's a great question. So it was for a number of years. So a lot of these applications, we have to collect data over years. So the data set was collected by Professor Sammy Kanal at Ohio State, one of my PhD committee members, at one of their agricultural farms up in Worcester. So most agricultural data, you have to get it from, you either have to go get it yourself, or you have to get it from somebody who's been collecting it for a long period of time. And so Sammy was working with the Ohio Soybean Council, I believe, at the time, trying to build a model for this defoliation, and her and another researcher, Jayson Zhang from Ohio State, and I he was able to make the model, and then we worked together to put it on our drones and deploy it out in the wild. But yeah, it's years and years and tons of time labeling. Actually, there was a period in time where me, Jayson Zhang, and a few other graduate students in our lab were trying to label thousands of images over like a period of a couple weeks, and we had to make a program that let us do it really easily. But I remember sitting in front of the TV watching The Office and just clicking buttons to try to defoliate it, not defoliate it, defoliate it, not defoliate it, so we could build our data set. It took forever.
Any other questions? We do have at least one question out of the YouTube chat, so hold on a second. It said, from RetroJet, I assume the military have priority over commercial airspace where their UAV program is, but is it possible that we may run out of safe, quote unquote, safe airspace and or have rogue operators causing accidents?
That's a really good question. To start from the back, we do have rogue operators that cause accidents. This happens all the time. Sometimes you'll see people shut down an airport because they flew a UAV into the wrong airspace. But actually, the way that our airspace is regulated, particularly for UAVs, is pretty tight. So airspace falls into a number of designations depending on the size of the airport involved. Most of the airspace around here is so-called Class G, which means that you can, it's basically undesignated. There's no airport that controls it. But anything that's Class A, B, C, or D, or E, you can't fly a UAV in because it's controlled by a tower, by an air traffic control tower. So actually, I have a big, if you ever come to my office, I have a big, giant 6-foot by 4-foot map of the airspace of New York, so I know where I can and can't fly. But usually, if you're out in an area like Binghamton, or if you're not basically in New York City or Washington, D.C. or Boston, you can fly your drone pretty regularly. And there are actually a number of apps. So if any of you guys like drones, you fly drones, always make sure that you download Lance, L-A-A-N-C, and before you fly, those apps will tell you if you can fly in the area where you are. They'll let you get a permit from the FAA, which you're supposed to do. Not everybody does that, but you're supposed to do that. They'll tell you if there are medical helicopters in the area, if there are planes in the area, if you're part of a military training route. They'll tell you all of that stuff. And you'll know for sure that you're allowed to fly there and you won't get in trouble. So I recommend if you're going to fly a UAV, this is what we do. Also, if you're going to fly on private property, always be sure to ask the person that owns it. I believe Vestal doesn't have any ordinances on UAS, but I'm not 100% on that. And so usually, as long as you're in a public space, it's pretty safe to fly. We do a lot of flying at BU on campus. I don't recommend you come and fly on BU campus because they do not like it if you do that. So you have to get a permit from the right office and know the right people, and we are always sure to do that. With respect to the military, most military UAS flights are done on military property. So you don't usually see UAS flights happening for the military just out in regular airspace. They have their own airspace designations, and actually in New York we have one of 7 FAA designated UAS test sites at the old Griffiths Air Force Base up in Rome. And that is one where you can actually fly completely autonomously. You can fly on instruments. You can fly actually piloted. Very nice resource. And if you work in the UAS industry, it's great to go up there and fly. It's very fun.
All right. Any other questions here locally? All right. Oh, give me a second here. I do my Phil Donahue thing. I'm dating myself.
Not really a question, but just observation and a little shared information. We happen to be over the state line in Pennsylvania, and we're members of the Claverack Rural Electric Cooperative, and they are already using drones rather profusely to monitor their lines.
Oh, yeah.
For storm damage, trees, particularly the ash trees, which are being killed off by the that ash bug that does that.
The emerald ash borer. You can see the evidence of that from the air.
And and so and just last year they hired a specialist to operate the drone and to survey their lines and just set up sort of within the cooperative, I guess you said a one-man department who really is almost autonomous from the rest of the place, just to gather the information that the drones can provide and pass it on to the linemen, and oftentimes during storms and so forth, when the linemen are out, if the weather gets so they can get a drone out, they know almost immediately where to go to do the repairs and clear the trees and so forth that are needed.
Absolutely.
And they're doing regular monitoring just because squirrels get on the lines and short circuit a transformer or something, and they can they fly the drone and they know where to do it. And likewise with replacing poles. So I just say it's a very practical thing that the drones can do a lot of help for.
Yeah, it's really great because they, it's being a lineman is dangerous, right? It's an extremely dangerous job. And if you can get more intelligence, you can sense the environment that you're about to enter, this, where are these lines, what's wrong with them, then you can get information that might save your life. We see this with forest fires, with all sorts of different very dangerous applications, and infrastructure inspection. Actually, bridge inspection is another really serious one. So there are very few bridge inspectors across the country, and we're seeing this push to utilize this technology to speed up the inspection process for bridges, make it a little bit more safer, more sensitive, because we absolutely don't want to see bridges collapse. We don't want to see people hurt in electrical accidents. We don't want to see forest fire workers getting hurt in the line of duty. So using these technologies to sense these dangerous environments is very, very potent. That's something that I really want to see more of, and I want to work on myself.
All right. Any other thoughts or comments? Well, if not, here we do. Okay.
So is there anything that we as your local and non-local community can do to help you with your research?
Take pictures of spotted lanternflies. If you see a spotted lanternfly in Broome County, don't send them to me. Send them to the New York State Department of Agriculture. The New York State Department of Agriculture is a close collaborator, and one of our machine learning models is part of their filtering system for the spotted lanternfly input data. If you send them a picture that you take of a spotted lanternfly, that will end up in my lab. We will have that. We will label it. We will use it to make our drone smarter. If you find a spotted lanternfly, tell them where it is, and specifically send them a picture. We really want to see that. Please, 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 please do that.
All right, citizen science, go get them. All right, well, Jayson, thank you so much for a really extraordinary talk. And again, it's just, we are so fortunate just to have Binghamton University here doing such a wide range of research, and we'd love to have tell your friends.
Of course.
Give me a call. We'd love to continue to share the research with the community here and those watching on the live stream. So
absolutely.
So we have a rule here at Kopernik that you can't leave until you look through a telescope. So the clouds have been sort of in and out, but is the moon still up? It's in and out. But so I say it's worth going out and taking a look, especially if you've never looked through one of our scopes. It really is an extraordinary experience. And so I invite you to, we have some members of the Kopernik Astronomical Society, the astronomy club that's resident here. We'll be happy to take you through that and maybe even give you a tour of our 20-inch imaging scope. Thanks again. Next week, we are going to actually return to talk about astronomy. We actually have a researcher from Johns Hopkins Applied Physics Lab talking about the Europa Clipper, which is going to be a mission that will be going to one of the moons of Saturn that will look at and try to figure out what's going on in Europa. So that'll be next next Friday. Again, if you can't make it here, we can watch it on our YouTube live stream. And if you wanted to watch this again, go to our YouTube live stream because it has been recorded. It'll be up there as for that matter, the last 4 years worth of Friday night programs. So look forward to having you come back. But before you do, head out to the scopes. Yeah. Thanks.
One of my students is interning at APL right now. Oh, really? Yeah.